Do you remember which one was yeah.
You.
Expressions for you.
You, yeah.
What's that last line?
Okay, so this is chapter 18, and this sort of mirrors the chapter 14 on work energy and conservation of energy. Okay, so the same concepts but applied to rigid bodies. The expressions over here, you've probably seen most of them. The principle of work energy is written right at the beginning. T1 is U1 2, which is the work done equals T2. So you're looking at what happens when a rigid body moves from point 1 to point 2, where the 1 and 2 represents two unique time instances. Okay, this is probably the only thing which is new when you look at it when compared to chapter 14, that is the expressions for the kinetic energy. A particle can only translate, while rigid body can translate as well as rotate. So these expressions for the kinetic energy are specific to those three cases we've talked about in the previous chapter on dynamics or equations of motion. You can have pure translation, in which case there's only kinetic energy due to translation, half mv square. If it's rotating about a fixed axis like a pendulum, no translation, then what you do is you take the inertia about the point which is fixed, IO, and multiply it with omega square, so half I omega square. And then general planar motion is example would be a rotating disk where you have kinetic energy due to rotation as well as kinetic energy due to translation. So there are two terms. Okay, this is the more general expression. You can derive the other expressions using the third one, general planar motion. The expressions for work done are similar to what we've done, but the same ones as we've done in the past in chapter 14. There is spring work, always negative. Gravity work is, the convention is mg is when it's down, y is up, so it's negative. In general, if force causes motion in the same direction, then the work done is positive. If force is one direction and displacement is in the other, then the work done is negative. And so work done to force, work done to movement. So using all these, we can now solve problems using these principles. So here is first problem. The 10-pound sphere starts from rest at theta equals 0 degrees and rolls without slipping down a cylindrical surface which has a radius of 10 feet. Determine the speed of the sphere's center of mass at the instant theta is 45 degrees. So we need to find the speed of the sphere. By that I'm assuming it's going to be the linear speed. Okay, so first of all, why is this a problem in this particular chapter? Why not equation F equals ma? Well, you're given some information at theta equals 0, and you're given some other information at theta equals 45. So you got to do this apply. Well, it's not about one instant of time like it is for F equals ma chapter. It's about two instances. That's one hit. The other thing is, remember when I talked about that algorithm for solving problems, there are those three steps. When you ask for velocity as a function of displacement, so find v when theta is 45, you go for work energy or conservation. In this case, both of them actually give you the same answer. You can use work energy or conservation. We're going to talk about conservation of energy in the next section, next lecture. Okay, but for now, let's use work energy and solve this problem because of the reasons I mentioned. So, principle of work energy. So let's write down each of those quantities. T1 is the initial kinetic energy when the ball is, or the sphere is at 0 degrees, so that's going to be 0, no kinetic energy, no kinetic energy because it's at rest. T2 is the kinetic energy when the sphere is at theta equals 45. Okay, so this is, so remember there were three expressions: pure translation, pure rotation, and general planar motion. Which of these three cases does this fall under? I need that in order to write the formula for T. Is it pure translation? It's not, right? It's rolling. Is it pure rotation? It's not actually rotating about a fixed axis. It's translating and rotating. So that's a general planar motion problem, which means I need to use the expression for general planar motion. Okay, this is again taken from that formulas I wrote earlier. Okay, so in this case, you'll be given IG, enough to memorize. IG for a sphere is 2/5 mr square, and the rolling condition is the velocity of the center of mass is omega times r. So think of it this way: if this is the velocity of the center of mass, then this point is at zero speed, omega, so v equals omega times r, where r is the radius. That's similar to acceleration of the center of mass is alpha times r. If you take the derivative of this, you'll get a equals alpha r. So let's put these expressions in T2 plus half 2/5 square let me write this as, let me sub in for omega. I'm not interested in omega. So omega is Vg divided by r. Okay, so I can cancel a few things. This r will go with this r, and so I'll end up getting, simplifying everything gives me 7 divided by 10 mv square. Okay, so I got the kinetic energy. Let's now solve for work done. Now what I suggest is the best way to find work done is to, well, work done comes from forces, right? F, dr, springs, gravity, so on. I recommend drawing a free body diagram because that will show all the forces acting on the system, and then you'll be able to reason out whether that force produces work or not. So a free body diagram of the sphere at a generic instant is going to look like this. So as a normal force, there is mg due to gravity, and remember, if it's rolling without slipping, there has to be a friction force. So that friction force is okay, so there are three forces: mg, friction force, and normal force. Okay, so that will help me write U12. Now, the normal force acts at the point of contact. Okay, and the point of contact at that instant does not move. So the work done, well, it doesn't move in the vertical direction, right? Or a direction which is normal to the arc, the circular arc. So the work done by n is 0. Friction force does no work either because the point which is in contact is always at 0 speed. So the only force which does work is actually mg. So we need to find the work done due to mg, and the expression for work done due to mg is minus mg times the difference from those two instances, 1 and 2. Okay, so we need to find what's the change in height of the center of mass in going from the topmost position to the bottommost position. Well, 45 degrees. So let's call that h. So mg is downwards, and the displacement is also downwards. So the work done is positive or negative? What's the work done? Is it positive or negative? What is the sign going to be? Negative? It's going to be positive. Because if mg is acting downwards and the displacement is downwards, force and displacement are the same direction, the product is going to be positive. You can think of mg is minus with the negative sign and h is with the negative sign, because both of them are downwards. So I just need to find h and I'm good to go. So let's find h. First, let's find the height of the center of mass when it is at the apex, which is going to be the radius of the bigger circle plus the radius of the sphere. Okay, next what I'll do is I'll try to find this height. So the height of the center of mass at when theta is 45. And so if I can find that height, then I can subtract r plus r from that height to get the difference, h. Okay, so you see that if this is small r and r, then this height is r plus r times cosine of theta. This length, cosine, that height, cosine would give me this length. So U12 is mg r plus r minus r plus r cosine of theta. And so we're all set now to put these expressions in the original expression from 1. T1 is 0, U12 is mg. I'm going to pull the r plus r common. 1 minus cosine of theta equals 7/10 mv square. M cancels off. I believe all these things are known. R is 10, small r is 0.5, theta is 45. Velocity is unknown, so I can solve for velocity. It comes out to be 11 point, and gravity is 32.2, so 11.9 feet per second. Yeah.
Can you explain why friction does not work?
Yeah.
Because like it's going over, it's traveling a distance.
Yes, but at that instant of time, friction, the point of contact has zero speed. And so one way of thinking of that is f dot ds, but other way to think of that is it's actually something called power, which is force times velocity. We did not teach that in the physics, and the integral of that is actually the work done. And so since the velocity is 0, the work done is 0. It's not, if it was sliding, if that point was sliding, then friction would do work, like a block moves this sliding. But if it's 0 speed, then think of it's f dot ds, but that ds at every instant is going to be 0 because velocity is 0. because f dot ds, right? F dot ds is f dot ds is v dt. Maybe here's a better way to think of it. Friction force times ds. We're trying to find if what's the work done by the friction force, but ds is v dt. That's just but v is 0, and so work done is 0. Okay. Any other questions? Okay, let's see if you can do this problem. That 80 kg wheel has a radius of gyration about center of mass of 0.4 meters. Determine its angular velocity after it has rotated 20 revolutions starting from rest. So you're given the displacement here, 20 revolutions starting from rest. Twenty revolutions is 20 times 2 pi, or 40 pi radians. Right? So find the speed. You got to use obviously principle of work energy. T1 plus U12 equals T2. Okay, so T1 is clearly 0. T2 is, it's going to be half I omega squared, right? In this case, this is a rotation about fixed axis. So okay, so let's put in the values. T1 is 0. T2 is half k omega square. K is given to be 0.4. So 0.2 omega square, and then U12 is the work done due to external forces. So again, draw a free body diagram for the disk F. Since I removed the pin joint, I would have a force V and force H in the horizontal vertical direction, and so those three forces could potentially do work. Turns out that H and V do no work because the point O does not move. There's no displacement, so the only work done is due to due to P. So the work done by P is, in this case, P is going to induce a moment about point O. So P times R is the moment, and since it's always at 90 degrees, it is P times R times the displacement. So theta 2 minus theta 1. The initial displacement we're going to assume is 0. So P is 50, R is 0.6, theta 2 is 40 times pi, and so we can sub this all in 1. Something wrong? I'm forgetting the mass. Yes, there is a mass here. So it's 80 by 2. So that'll be 16. 6. Isn't it 16? Oh, I forgot R squared. Good catch. So 6.4. Okay, solve for omega gives me 24.27 radians per second. Okay, any questions? It's really straightforward, right? As long as you can find the expressions. Okay, so last question and for today.
Do you have the phone?
Yes.
Okay.
Okay, the pendulum consists of a 10 kg uniform disc and a 3 kg uniform slender rod. So it's 3 kg. If it is released from rest in the position shown horizontally, determine its angular velocity when it rotates clockwise 90 degrees. So when it rotates clockwise 90 degrees, it would be right like this. So again, the key to figuring out this is a problem involving work energy is that you are given some information at one instant of motion, that is at 0 degrees, and you're told to find something else, the speed, at 90 degrees. And so when you ask to find speed as a function of displacement, in this case 90 degrees, you got to apply the principle of work energy or conservation, which we're going to talk next lecture. So principle of work energy. T1 plus U12 equals T2. Since the rod starts from rest, T1 is 0. T2. Okay, so for T2, we're going to first figure out this is pure translation, pure rotation, or general planar motion. Since the pendulum is rotating about one axis, it's a problem in pure rotation. So we need to find the inertia about A. So half I A omega square. So I'll have two parts to it. There is the rod, and then there is the disc. Okay, so the inertia for a rod about axis A is going to be first the inertia about the center of mass. So that's, and this will be given to you, it's mass of the rod times length squared divided by 12 plus by the parallel axis theorem, it's going to be mass times the distance from the center of mass to the axis A. So L divided by 2 square. For the disk, the inertia about the axis, first you need to find the inertia about axis G2, which is, again, it's given to you, it's half m disk, the radius squared, where the radius is going to be this, plus by parallel axis theorem, we need to find the inertia about A. So mass of the disk times the distance from G2 to A. So that's going to be the length plus the radius, right? Squared. So everything there except omega square is known. But that's the unknown, right? And so the last step is to find the work done, U12. Again, a free body diagram will help. So I'm going to draw a free body diagram of the system at a generic angle theta. I replace the pin joint with a horizontal and a vertical force. There is gravity, M1, let's call that M rod G, and M disk G. So there are 4 forces, but turns out that the work done by H and V is 0 because the point A does not move. So the work done by, I think I'm forgetting another force, that is a moment. Okay, so work done by the moment is m times the displacement, so pi divided by 2 minus 0, because the angle turned is 90 degrees, so m times theta plus work done by m rod g is going to be force times the displacement. So m rod g is downwards, displacement is downwards. It displaces by a length equal to L divided by 2, right? The center of mass goes from G1 to here. So the displacement is L divided by 2. And the sign on that is positive because displacement is downwards, the force is downwards. And finally it is M disk times G. The displacement of the center of mass is L plus R. So again, in this, everything is known, and so we can plug all that together. We can solve for omega, which is the unknown. So omega comes out to be 3.16 radians per second. Okay.